Okay, looks like we're live. Okay, so ladies and gentlemen, I wanted to hit on topics discussed in this chapter 3 of functional programming in Scala that I had asked you to read. This chapter is entitled Functional Data Structures, but it actually covers a cluster of sort of related concepts as well. I wanted to have a discussion around these and to make a number of points related to this. So we're going to be using the Scala shell to explore, so I would invite you in this discussion to call up your Scala shell, and I will do so myself. And then I would suggest that you that we start with activities. Okay, this is the Spark shell. We don't want to do that. That is your destiny, but it won't be. It won't be yet. Okay. You'll not see its beauty for another couple weeks. Okay. Oh. Okay. I see. It terminated out of it. Oh, that's a fun thing. Okay. Scala. There we go. Boom. Okay, so we're going to start up Scala because we're going to be undertaking some examples related to the book. That's a really interesting dysfunction. Okay, so let me go back to this. So the first thing that the book talked about was focus of the title of the chapter, just defining functional data structures. What do I mean by a functional data structure? And how is it different from other types of data structures? First of all, give me examples of what data structures.
Linked list, hash table.
Hash table, good. Binary tree, heap, stack, red-black trees. This whole set of data structures that we employ in computer science. And for those not from computer science background, the students who have not seen 280, for example, I would actually recommend taking that course. I'll be working with you. I didn't want to overload you to the term, for the term. Cheyenne and Yangqing and Rifat. I didn't want to overload you, but actually there's a lot to learn in 280 and then in 360 about sort of the running time of algorithms operating on traditional data structures. But what do we mean when we talk about immutable data structures or functional data structures? Kind of giving it part of it away there. What
functions?
Okay, certainly said data structures involve functions. But when we say functional data structures, what's one key attribute that distinguishes them as a functional data structure?
It's defined exclusively by or completely by its inputs.
Okay. Inputs and?
Well, the logic within the function, but it's immutable, so it doesn't.
Aha. What's immutable? The
data structure.
The data structure is immutable, ladies and gentlemen. We're not mutating memory. Hence, immutable data structures. So when we say a functional data structure, first and foremost, what will come to mind is immutability. They're not changeable. There's no aspect of state that gets updated. That there's a new item inserted into an existing tree, or there's an extra link placed at the end of a linked list, or an extra item placed atop the stack, pushed onto the stack, as we say. Instead, so how does it function? If we're not modifying the data structure, what happens? And this links it in with the notion of a function. What happens? If we're not modifying the data structure, how is it that we realize any sort of change at all?
Create a new one.
Yeah, we create a new one. So if we need a different one than we have, rather than modifying it out from under us, we create a new one. and we return that, right? So with a function, we have inputs and outputs that are well-defined. If that function has no side effects, the outputs are a well-defined function of well-defined result of the inputs. And here with functional data structures, we end up, when we want to modify something, returning a new one. Now, we have to be cautious about this word new, because what we're returning is not always built from scratch. It's not always built from the basics up. Why do I say that? Gets to my second point here. Why do I say that? Suppose we append one linked list to another. If they're immutable, what can we do here? So let's go into Scala. Here we are. Let's go over here. And how do we declare a linked list in Scala? Anyone? Well, you saw sort of a nice little list data structure being defined as part of this chapter. The authors wanted to kind of give you a sense how you build it from the ground up. So actually on page 30, they provide this definition of list, right? And we'll come back to that. And then down at the bottom, they define some constructors for this. This is what we call an algebraic data type. And these jointly define sort of the building blocks for these overall lists. Now, one of those building blocks is cons, which is used to construct a pair. Okay, but in Scala, lists, they're also built-in lists. So let's try to define a built-in list, right? Val my list. Here we go, right? Okay, and let's create a list of foo. You could choose your own name, and bar. Okay, there we go. Oh, okay, bar is not a member. Oh, okay, yeah, okay, sorry. What do I have to do here? What did I forget? Oops, nil, not null, nil. Okay, there we go. So, ladies and gentlemen, here we have a list of foo consisting of foo and bar. You notice we can kind of describe it either way. Okay, I could have just written this out with these things quoted, of course, or I could have written it this way. Okay, and so if I do mylist.head, what will I get back?
First one.
Good. How if I do mylist.tail?
A list of the last one.
Indeed, a list of the last one, list of bar. What's this nil thing?
Terminator?
Yeah, so ladies and gentlemen, we have here a list. It's called my list, right? There we go, my list. And it's pointing to foo. That's kind of the first half of it. And for the tail of that one, it's pointing on to bar. And for the tail of that one, it's nil. This is nil, right? There's nothing it's pointing on to. And that's what I wrote here, okay? Okay, so ladies and gentlemen, here we have a construction of a list in this way, and we have an alternative way of specifying that list if we wish to do so. Now, suppose I wanted to add on Baz to the front of this list. Okay, my list 2. Okay, and I wanted to add on Baz onto my list. Does this have to create an entirely new list from scratch that consists of Baz? Does it have to, in other words, create this? So here's the first list up here on the board, and I apologize for the internet listeners out there, but we have drawn here 2 parallel lists, and one hypothesis is that we're creating a whole list out of scratch, out of whole cloth, we have this, and we have foo, and we have bar here. Is that what happens? That it creates this set of from scratch? What can happen instead? Okay, yeah, it reuses my list. Okay, so rather than rather than creating it entirely anew, having to allocate all this memory, having to go get this memory, get that. For those who know C, doing calyx for these things beneath the scene. Instead, what can it do? It can reuse this other list, right? It can point here to that guy instead. Now, why can it do that? Why can it do that safely? Why can it just reuse it instead of creating a new one? Well, one of the foremost reasons is it doesn't have to worry that someone else through this one is going to modify this one out from underneath it. After all, if these were immutable, if you could change bar to be zap here later, then someone modifying my list would be modifying automatically my list too if they shared data. If my list too just pointed for its later elements to my list, someone modifying my list would inadvertently modify my list too. And I'm going to, in fact, make this point even more directly here. I will say, okay, this is foo, followed by bar, followed by nil here. And I'm going to put these things around it just to make it very clear what we're doing. I would argue that this list here can simply make use of my list. For this element, we could just point directly to my list because there's no risk that it will change out from under us because these data structures are immutable. They can't be changed. So the fact that they can't be changed allows us to reuse elements of them in a fairly free way. Now that's very significant when it comes to this property of immutability of needing to return a whole new list when we have an operation on an old one. We don't have to actually create out of scratch. We can often engage in a whole lot of reuse through sharing. We can have shared data structures. And in fact, this goes on a lot with the domain of what's called value objects in object-oriented programming. We create immutable objects for a couple reasons. They're easier to build. It's easier to build other objects out of immutable objects than out of mutable ones. Because if you're building out of mutable ones that can change, you have to protect yourself against the change by copying them. And often it means copying them many times whenever you pass back a reference to them, for example. Whenever you're given a reference to them, copying them. Whereas with immutability, ladies and gentlemen, that is not an issue. So immutable objects end up being very natural building blocks of others. They're also easier to reason about. We can reason about them without worrying someone else will change them out from under us. We can reason about them in a way that's called, is associated with referential transparency. It's associated with equational reasoning. It's almost a mathematical form of thinking about them. When we have an expression, we could substitute in that. When we have a definition, A equals some expression, we could just substitute in that expression where A appears. Okay? So data sharing turns out to be a key aspect of creating immutable data structures that are efficient. Okay? It turns out that immutability is also going to help us a great deal in the modern era because of its interaction with what? Does anyone want to put forth a guess? When do we really, really have to worry a lot if someone else is going to change out an object from under us? Parallel computing or concurrent programming, which may be parallel. Literally, things may be running at the same time, or it may just be that it's switching off between two threads. Sometimes this thread runs, sometimes that one, but they're running at the same over the same span of time, just at no one time, on each time only one of them is running. So when we have this sort of concurrency, when we have several running at the same time, there's a lot of worry about if I'm in one thread and I'm reading something that someone else might change it. So what do we do when this happens? Well, we engage what are called locking protocols, which basically mean, for example, I lock it for a certain amount of time that I need it, and no one else can write to it. Then I might release the lock, someone else can write to it. There are these things called synchronization mechanisms for parallel computing. And it turns out with immutable structures, you don't have to worry about that issue, this issue of someone's going to change out from under you in a different thread. More than that, the dependencies are clear. What you're depending on is often much clearer because you don't have these references into things which are less clear through side effects. This function may depend on some aspect of global state. Instead, what it depends on is the parameters to that function. Okay? So immutable data structures turn out to be really, really valuable and useful. And in object-oriented programming, we often make use of objects that are immutable because it's easier to build things out of them. It's easier to reason about. You can much more easily demonstrate correctness by specifications, by saying, what does this do? Often that's much easier for an immutable object. So they have many virtues, and there's some lectures of me talking online where we'll talk about immutable objects, what are called value objects in an object-oriented framework. Okay, so let's talk about this definition on page 30 of the list. We have here, ladies and gentlemen, a definition that has several parts to it. Okay, one up here, I should really create these into slides, but up here it says sealed trait list of plus A, and we'll get back to the plus and what that means. So that's actually effectively a definition of a class for list. Okay, now traits are a little bit more sophisticated than classes. Anyone who was in my 470 class, 816 class last term may remember. What can we do with a trait that we can't do with a class? Does anyone remember?
Inherit it or something?
Yeah, we can inherit from multiple traits. We can weave them together, mix them together like mix-ins. It's a very, very flexible thing. And not only that, you can have one implement things that end up being used by the other. But if essentially we have sort of a definition of a class here with list, okay? And then we have an object called list. What is that object? This is talked about later in the chapter where we talk about companion objects right there on page 33. It's talked about companion objects. What is a companion object? When it says object list, and we've already defined a trait or class called list, what does that object list provide? Well, it's more than that would suggest. So it provides, ladies and gentlemen, a set of methods set of ways for manipulating lists that don't depend on any one list, rather they're associated with the whole class. And here we have a set of methods that are basically utility methods for operating on lists in a functional way. So this object list declares things that in Java or C++ we would call what? A companion object defines things that are called, okay, we're going to have to play hangman here. It ends with an S. Sorry, it begins with an S. It ends with a C. It has 6 letters. It has 2 T's in it. Okay, I think this man is going to die by hanging. it has an I, the second to last letter. Oh man. Oh man. Doesn't make me feel uncomfortable. Okay. Okay.
Static.
Thank you. Okay, you saved him. You saved him. Ladies and gentlemen, it's static. What do I mean by it's static? Unfortunately, this is a horrible term. This is one of my most disliked terms in the programming language of the modern era, because it means something that is very specific to computer science programming languages. What does this mean? If we say something associated with a class is static for Java, for C++, for Objective-C, what does it mean?
It's observable inside the class.
Well, okay, so if we had a class A, and we had, this is Java, this is not Scala, far be it from Scala, okay, and we had static int A, what is foo? Well, that's not an int, okay. Okay, one, okay. What does it mean that this is static in Java? This is Java. What does it mean?
Constant.
Well, it's not that it's constant. We could say final. It would be actually constant. But you're getting closer. What does this mean?
This thing is not associated with instance.
It's not associated with an instance of the class, not with an object of the class, not with a particular thing allocated from the class. It's associated with the class itself, with the class A. There's only, to put it crudely, there's only one of them for the whole class. There's only one value for this. And if we change it by incrementing it, ladies and gentlemen, there's only one of them for the entire class, okay? So the companion object in Scala is a cleaner way to do that. And it gets rid of this notion of static. Why do I dislike static? Because static in most areas of science is used in contrast to what?
Dynamic.
Dynamic. And this says nothing but, I mean, it's a great thing Tina suggested, that maybe this, you would think static means it's final, it's constant. You would think. But computer scientists who created that language screwed it up. Okay? And I will take response. Well, okay, I didn't do it.
You might want to rename it as uniform.
Huh?
Yeah, you mean like uniform across all instances.
That's right.
They share the same value,
Yeah.
or shared, or, you know.
Yeah.
Yeah. In any case, yeah, you would think it would mean, by all sensible notions, it would mean a fixed value, a unchanging value, but it doesn't. Alas, it means it's class wide. So a companion object, ladies and gentlemen, is defining this object list here. That's defining things that are used for the that apply sort of to the whole thing of lists. So, ladies and gentlemen, when we say this, when we say, for example, list of zap and bar, like that, this is actually a method in the companion object. We're not calling it any particular list. We're just creating this, okay? So we often define companion objects. In this companion object, it defined a sum, it defined a product, and defined apply. Okay, let's talk about those, right? Let's talk about those. So these were defined here as sort of nice functions that take in a list and return a value. Okay? And you notice one of them was defined for ints, very specifically, and one was defined for products. Fair enough. And those were given as little examples, because after all, we weren't sure that if we defined product for any type, a list of anything, that there'd be a multiplication operator. or there'll be a sum operator for any type of thing. Fair enough. But we define those operations there on that class. Now, in order to define the operation, we ended up using a match construct. This is not a small matter. This is not just a matter of a little curious thing. Here we're saying case object nil. This is page 30, right? Case object nil. You see that? Case object nil and case class cons. Do you see that? Okay. What are those things doing? You could be mistaken for. You could be excused for sort of being confused about those. So what are those doing? Sorry? Yeah, they're constructors. They're essentially serving as constructors, which is pretty interesting. You may not have seen that sort of constructor notion before, but they're actually sort of extending the class or extending classes, list of nothing or list of A. But they're also serving as constructors of sorts for this class. So we can have a sort of a cons class, which brings together a head and a tail. That's what I've kind of drawn up there as instances of the cons class. Or we can have nil, which is kind of a singular object. It's called object, case object nil, and it's kind of a singular thing. And you'll notice it's not specific to any one type. So it's a list of nothing, and it applies to all of them. And then we can use those to build instances of the class. Cons A, cons B, look at page 31, where we build up little elements of things, okay? Now, how does this pattern matching work? Well, we've talked about it before. How does it work? Can anyone remind me? So let's look at that pattern matching on page 30. So can anyone describe basically what's being characterized by the sum rule? Anyone want to say?
It's kind of breaking it up into head and tail.
Good. We're defining sort of a base class, a base case, where we're dealing with nils, right? Nil is 0, and absent that, we have kind of an inductive case, right? Case where we have at least one element in the class. The first one handles this case, right? It's a recursive function. It's a function that's recursive. So, yeah, we'll handle a base case, and then we'll handle a case that needs to decompose it into at least one thing, and then delegates that function for the rest of it, right? Call sum for the rest of it, right? X plus sum of xs. And you'll notice that that's a recursive call. This definition of what sum means, it's not circular, it's recursive. How do I make that distinction?
Because it gets smaller every time you call it.
Every time you call it, it gets smaller. The Hamiltonian decreases. Well, not quite, but it's going in a certain direction, so it gets smaller and smaller. It breaks it up, it divides and conquers. It breaks it up into smaller pieces that it then goes and solves successively. Okay, so we have a base case, handle the case where it's nil, and then we have a case where we're dealing with an object that's a pair of things, right? X and XS. And the rule for that adds the value of x to the sum, the same function, applied to the tail. Are people comfortable with that? Yes, Kurt.
Is there a way to do this so it's tail recursive?
Yes, there is.
'Cause this isn't really going to be efficient, right? Okay.
Yeah, well, yes.
Like if you can do recursion, tail recursion, isn't that always better? Like uniformly always better?
Performance-wise.
Yeah.
Yes, but a compiler can do it for you sometimes.
Can convert it?
Yeah.
Though tile recursion does break the definitions of list, like the list type, it naturally was right associative.
Yeah.
While you do tile
This
recursion,
is
it's
true.
hard for you to pretend a right associative. What you actually do is the left associative.
Yeah, that's
So-
true.
But it's good in most of the cases in the sense we have
Yeah.
the list with the unified type.
Yeah.
So we can use that they are associative. So
Yeah.
we can turn.
Right, exactly. Yeah, I think
Huh.
when there was a deep conversation, you made some very good points there, and I don't want to overwhelm other people yet, but we may return to this issue. Okay, I'm trying to build up some basics here, but these are very good points. So later, in fact, I think in chapter 2 there was a discussion a little bit of tail recursion and tail calls in Scala on page 20. If anyone is interested in pondering what Winchell spoke, you can go look at that. Judging by the reaction of some people in this class, I didn't want to go too hard on that quite yet. Okay, tail recursion is a topic that requires a little bit of comfort with recursion before you can understand it. But do people understand how this recursive call takes place? I want to highlight the fact, a couple things about this. First of all, it's functional. You pass in a list and it returns back an integer. Second of all, it is recursive. So to solve the function, it breaks it down into pieces and solves each of them. And there's some base case. There's some bottom there. It's not turtles all the way down. Okay. Thirdly, what we have here is fairly declarative. What do I mean by declarative here? This is a recipe of how to perform a sum. We'll get to how to perform a product in a moment. But thank you. But it's fairly declarative. What do we mean by that? We're specifying kind of what we want to have happen, and we're not concentrating on all the details of how we say, well, look, for a case of an empty list, nil, the sum is 0. For the case of a list with at least one element, with a pair of elements, we add whatever in the head of the pair to the sum of the rest of the list. It's fairly declarative. It kind of says, for this case, this is the situation. For this case, this is the situation. For this case, the sum is 0. For this case, the sum is this other thing. In contrast to kind of writing a loop, which starts to get very specific about the ordering that you might want to use, etc. Here we have a fairly clear, transparent description of an algorithm, of a way of sort of characterizing what does sum mean. Okay, so we say that pattern matching here allows for more declarative programming. This is an example of that. Let's go on now to a more advanced thing. Not tail recursion, but product. Okay, so can anyone tell me what does product do here? And what's one trick that it accomplishes? So product has 3 terms, not just 2. Can anyone help me understand product?
Well, it makes a definition that says if there's nothing in it, it's just 1.
Okay,
Which
if
is
there's
kind of an arbitrary definition, but
fair enough.
yeah.
Fair enough.
And then
yeah.
it says anytime there's a 0, anytime it finds a 0 at the head,
Yeah,
then the whole thing is 0.
because
0 times anything is 0.
0 times anything is 0, so it sort of short circuits at that.
Presumably you can't have an infinity in there someplace.
Exactly. Yeah.
And then the next part is it just looks to say head, tail. Well, take the head and multiply it by the product of the tail.
Good. Are people comfortable with that notion? This notion of recursion there, and this notion of a short circuit where it realizes, oh, wait a minute, anything that starts with a 0, it's got to be product 0. And Kurt raised an important point. We're assuming there's no infinity later in it, but fundamentally, that's what that represents. So what's the use of the underbar there? I've said that underbars in Scala represent an uncomfortably large number of different things.
Anything.
That means anything there. It doesn't actually mean like there's a function to an argument there. It just
Literally
Underbar God.
it
Yeah.
yeah, it matches anything. And basically not only matches anything, it matches anything and throws away the value. It says, whatever it is, don't pay attention to it. The value is 0. Are people comfortable with that? Comfortable or not? Okay. Well, if you're comfortable with that, let's try writing a function, shall we not? Right or not?
Right.
Okay. Good. Good. Well spoken.
Tight.
Well spoken. Okay. So, ladies and gentlemen, let's for the greater good, let's define ourselves a function. Okay. 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 Now, for simplicity, we're going to do this first without type parameters. Okay. First, in the absence of type parameters, we're going to define a little function that is going to join together a list with a separator. And we're actually going to do it not with the definition of list here, but with the definition of list built into Scala, with these double. This is how you indicate cons in Scala. Okay, it's with this. This sort of joins together. This appends this to the rest of the list. Yeah. Okay. So def my join. How's that? Okay. And for simplicity, we're going to take in a list of double. And we're going to call this L. Notice I'm hewing to a different naming convention than I want. Right? I'm going to call it L for now. And I am going to say, okay, now I fail. Strusep, which is a separator. Okay? And this is going to be a string. Okay? Great. And this is going to return back a string. Are we okay with that?
Yeah.
And we're going to say equals here. Okay? Okay. Okay. And there we go. And the first thing I'm going to do is I'm going to say, okay, we want to now take this and create a string that's the result of placing strusep in between every pair of values. So how are we going to do this?
What are we trying to do?
So we're trying to go from a list that will look like this. You know, a list of 1.0 and 2.0 and 3.14, etc. to minus 1.0. We want to create a list and a string from this that will have, it'll be a string, and in that string, each of these numbers will be separated by a given separator that we specify. So maybe a comma, in which case it would create a list like this. Minus 1.0.
So we need to do match, is what you're saying.
We can take the heads and tails and then
Okay.
or this means separator and then continue for the rest of the tail.
Okay. Okay, so let's think about how to do this. What do we need? Kurt said earlier we need, and it was implicit in your answer, what sort of construct do we need?
Match.
A match. What are we going to match? So we need to, when we say match, what are we asking to match? Are we asking to match stir-sep? No, the list, the structure of the list, ladies and gentlemen. So we're going to say L match, and we'll do begin paren, end paren. Begin, sorry, not end paren. Begin curly. Okay. And ladies and gentlemen, what should we match? Okay. What are the cases here?
No.
Okay, if we have nil, ladies and gentlemen, what are we going to give back?
Empty string.
An empty string. Good. Okay. Good. How about another case?
Use the cons.
Case sum.
Sorry. Okay. So
Can you just go x : : xs or something?
yes. So head : : So what would you like me to write?
Tail.
Head : tail. If we have that, what do we write? Is this going to be right?
I think put it in brackets or something.
Okay, well, I'm not talking about the syntax.
Oh.
Okay, what do you want me to put here as the rule? Let's suppose we were to put that. So if we have a head and then a tail, what might we put?
H.2 string.
Sorry?
Is there an H.2 string?
You can, if you want to return a string, you can plus it with another string, for example. Yes, there is a toString.
Okay.
But
H plus.
okay, H plus what? Stir-sep, okay. Okay, so
Plus my join on T.
okay, plus my join on T. Now this seems like a plausible idea, but what's the fly in the ointment? Okay, and then we'll finish off the definition. Oh, the grim truth. Okay, indeed, I forgot an emperor. Okay. Okay, so this is a bit more painful in the Scala shell, but I will persist. And there we go. Okay. Okay, and then this, and I should be dealing with nice. Oh, whoa, okay. Okay. There we go. There we go. And then here, right? Okay. Okay. Now, what's going to happen if we use this?
We have to pass the separator along.
Well, okay, I passed it along, but.
Oh, I didn't. Yeah.
Okay. Okay, so what if we do this with list of 1.0, 2.0, 3.0? What happens? What do we get back? Oop. Of course. Here. What do we get back? What's the fly in the ointment?
Oh, it ends with a...
Indeed. So how are we going to deal with this? So that was a valiant shot and a fine start. A fine start. What are we?
Another case.
Okay, and what does that case have to be?
H : : underbar.
H : underbar.
You want an empty tail.
I probably would just want nail in front of that.
A what?
Nail. H :
No. Oh yeah. Okay.
Nil. Yeah. Yeah.
That's right. That's right.
Ladies and gentlemen, here we go. Yes, Winchell has it. Okay, so we're going to have what here? Can you characterize it? Winchell uttered it, and he deserves full credit for the Winchillian idea. So what do you put?
H : nail.
Nil. Yeah. And what do we have then?
Well, just this H itself, to string.
Yeah, H dot toString. Now note we could put this or we could put that just by itself. And in Scala it's considered quite favorable to use it without just begin paren, end paren. Okay, there's a whole Scala style guide that's written. Okay, so now we have this. Do you think this will work?
Mm-hmm.
Let's try it.
Until we test it.
Okay. How if we have, just two of them? Okay, what if we have one of them? What if we have an empty list? Ladies and gentlemen, they call it engineer's induction. 1, 2, 3, infinity. Okay. It actually works pretty nice. Now, what's this colon going on here? What is this going on here? I mean, we introduced earlier, we saw how we could use these operators to build up lists, to cons them together. What are we doing here in the case of a match? What mystery lies before us? What meaning? What does this mean?
It's comparing the form.
Okay, good. It's matching the form. And it's actually deconstructing. You'll recall last time I mentioned this notion of extractors. So it's actually, ladies and gentlemen, it's unapplying here. Yeah, it's doing an unapply. It's figuring out the components associated with what? Each of these is attempting to see if what matches these things. So the result of calling unapply on what?
On the list.
On the list, the thing that's being matched. So it's calling unapply and it's saying, okay, is it of this form, of that form, of that form? Ladies and gentlemen, unapply knows how to take things apart and return, ladies and gentlemen, the constituent pieces. Okay?
And this is because it's functional and immutable and all that stuff. Well,
yes. I mean, if unapply weren't immutable, it would be a disturbing thing. But
so I mean, like
the notion of it is
like the list itself.
The list itself is
defined functionally, which means you can
take it apart.
Take it apart.
It doesn't hinge too much on that, and I don't think it hinges too much on that. But ladies and gentlemen, here we're taking it apart. These are the pieces that make up this list. We have head and tail. Here we have head followed by nil. Okay. So, by my aesthetics, I consider this thing a thing of great beauty as well. Okay, this is a beautiful little piece of logic, and by my token, it's a lot clearer than doing successive if statements, if this, if else that, etc. It's quite clear in its meaning, quite declarative. It says if under this situation we have this rule, under this situation we have this rule, etc. Okay, so ladies and gentlemen, pattern matching is a big component, and you'll notice that a lot of the pattern matching in this chapter made use of these subtypes that function, as Aiden noted correctly. They function as kind of constructors for this thing. They happen to be subtypes of it, but we're saying, okay, if we're dealing with a cons, this case class, then this certain thing applies. Where is it? If we're dealing with a cons, that thing applies. If we're dealing with nil, other things apply. Quite nice, and there's a nice discussion of matching that occurs in this context. Okay, so that's good. We'll come back to some more minor parts. Okay, yeah, please.
What's the plus A plus plus A?
That list plus A. Okay, so this is this covariance and type parameters that I was going to mention now, and it's a good thing. Okay, ladies and gentlemen, you'll notice that this function in the book, or this situation in the book, this sort of abstract data type in the book, you'll notice that it's defined in a type parameterized way. What do I mean by type parameterized? What do I mean by the fact that list is type parameterized? What do I mean by that? It's a fancy term. What do I mean by type parameterized? It's it's certainly very closely related to generics, or in C++ they're called templates.
The type
But
is defined.
there's a parameter that specifies what type this applies to. So the class as a whole can take a parameter that specifies, okay, is this a list of ints, a list of doubles, a list of floats, a list of chars, a list of whatevers, booleans. Okay, now why is, and so I'll come to Aiden's question, but why is that significant? Why is that a value? Why not just make it a plain old list that can take anything as its elements?
Polymorphic.
Yeah, okay. So through polymorphism, you could have a list that takes anything. And the very first versions of Java, which I remember rather well, 20 years ago, 21 years ago. You folks probably remember them less well. One of the notable things about Java back then is that it didn't have type polymorphism. It didn't have generics. And so you would just have a list, data structure, and that list took in, guess what, for elements?
Anything?
Objects.
Object
In Java.
which is anything in Java.
Any reference is a subset of object.
Right.
Not quite anything, because like ints and doubles, like these primitive types, are not objects.
That's right.
But capital I ints are.
Yeah.
Capital D doubles are. And so you would have just one list to rule them all. It would take objects in, and you could add them to the list. What's the problem there?
Well, you might want to specify only a certain type in your list.
Indeed. So maybe you don't want to have a list that sometimes says a few elements are persons, a few elements are elephants, a few references to elephant, reference to person, reference to deer, mule deer, reference to doctor. You don't want that. You want a list that you know is a list of doubles, or a list of ints, or a list of persons. And there wasn't an easy way to enforce that in the earliest versions of Java. Just have a list of anythings. And so you would end up building data structures around it that would enforce it. So you could only add an int for this one, and it would reuse it. So, ladies and gentlemen, one way to do that with these objects is through type parameterization. So you say, I have a list of doubles. I have a list of ints. I have a list of elephants. I have a list of persons. I have a list of doctors. Right? And that's what that type parameterization is about. You can have a list of a type. It contains that type. Its elements are that type. Does that make sense? Okay, now, what is the plus mean? Do you see what I mean? List of plus A. What does that mean? No, this is not a list of good students who get A pluses. Okay? What does it mean, list of plus A? Well, what it means, there's actually a little comment in it at the end of the next page. It's what's called
Variance.
Yeah, it's associated with the notion of variance and covariant and contravariant. Now, this issue comes up in 816. and those of you who take that course next term will see it, where we talk about covariance and contravariances in relation to what's called the Liskov substitution principle. But the basic question here, I'm going to try to boil it down to simplify the issue because I don't want to spend the entire remaining time on it. If we have a list of dog, a list of elephant, a list of horse, a list of monkey, are those subtypes of animal if elephant, monkey, horse, dog are each subtypes of animal?
It would be a subtype of list animal.
Of list animals, what I meant to say, yes.
Yeah.
So, in other words, if you have list of T, is that a subtype of list of S if T is a subtype of S? So, you might have elephant, horse, dog, monkey, all being subtypes of animal. Does that, if that's the case, does it automatically follow that a list of those, a list of monkeys is a subtype of list of animals? Now, why does this matter? Because if we had something which processed list of animals, maybe we admit them to our vet clinic, right? To our veterinary clinic, or maybe we add up their weights or whatever. If we had some function that takes a list of animal, can you pass it a list of monkey and expect it to work? Right? Can you pass it a list of, list consisting only of Curious George, for example? Or could you pass it a list of elephant and expect it to work? Does it accept it as a list of animal? And what this is saying with the plus there is that it does. So it's going to automatically make a list of monkey consist of a list of animal. It'll qualify as a list of animal. Now, there are times where you want covariance. And then there's going to be times where you, turns out, want contravariance. And we may see that in a later lecture, where you want subtypes, for example, for the arguments of their. So if you have a function and a subtype, that's an overriding of the corresponding function, a supertype. Maybe it's returning the mother of a given animal. And you have that function, it's called mother. And for animal, it returns an animal. It's a method on animal, and it returns the mother of that animal, which is an object. It's a reference to a what? To an animal. But if then you add mother for a monkey, the mother method would return a reference to a monkey. Could return a reference to a monkey, right? It doesn't have to be the same as for the supertype. It can actually be it can be covariant. We say the return value is covariant, in the sense that as you go down, as you get more specialized, as you get monkeys and you get elephants, they can each return a value that's specific to their type. Because it's, after all, an animal, right? A monkey, ladies and gentlemen, is an animal, okay? And an elephant is an animal. Yes, Winchell.
But does this lose the type such that, like, if you ask for the mother for a monkey, you can return an elephant? If you specify you specify the function to be like the subtype of animals.
No. It's this subtype of animal. It's this particular one. So if it's defined in monkey, you can return this dot type in Scala, and it will actually return. It knows it returns a monkey. But if it's something that's being used for elephant, it'll return an elephant. Okay, this dot type. You can look it up, Winchell. But ladies and gentlemen, by contrast, so that's covariance still. As you go down the hierarchy, as you get subtypes, they get progressively more specialized in this. By contrast, there are times you want it to be contravariant. Like
creator.
A subtype, if a subtype defines a function, also defined as a supertype, its parameters need to be as general as the supertypes parameters or more general. It can actually accept things that the supertype doesn't handle. But it has to be able to handle all things of the subtype. So maybe there's a method like there's a method called gets along with, and it takes in, for an animal, it takes in an animal and it returns Boolean, true or false. Gets along with, okay? So you could ask an animal, does it get along with another animal? Okay, so like a tortoise might get along with a deer, but a lion wouldn't get along with a lamb or something like that. Okay, okay. So ladies and gentlemen, so for an animal, it takes in an animal, but maybe a subtype. Maybe for a monkey, you allow gets along with to not only take another animal, it could also take a person. A person is an animal too, so that breaks down.
Say it's not a person.
Okay, yeah, you could say it's not a
animal.
subtype of person. So, or person is not a subtype of animal. So it might take a more general set of things. That's fine as long as it can handle all animals. As long as you could say, does the monkey get along with, does monkey get along with Huli Jing? Does it? That's fine as long as it can. As long as it can handle all animals, then it's fine if it handles additional things that animal does not handle, if you ask get along with. So it's actually contravariant. It can get along, it can take a broader set of things for the parameter than in the supertype. Okay, anyway, that's 816, and we won't spend the entire lecture on that. Okay? Okay. Ladies and gentlemen, recursion. Okay, we saw that. Abstraction via parameterization. We saw type parameters, and we saw, this is a very important point, later in the chapter. We actually saw that, ladies and gentlemen, in page 38. Recursion over higher order lists and generalizing to higher order functions. Right? We saw that we could take functions which are similar, sum and product, and we could generalize them. By handling more. By abstracting out what they do. Sum and product of the same basic structure. What they differ in is the initial value and the operation applied. And so that ends up getting generalized in what? The fold function. And then we can define sum and product just in terms of the fold function. And we don't have to write the code again. Okay? So this generalization by this abstraction by parameterization, which Gutag and Liskov write about so eloquently in the Red Book, Program Development in Java. This is an example of abstraction by parameterization. We basically have each of them, sum and product, just call off to a more general function that asks, okay, what's the kind of the initial value, and then how do you combine elements? That's what fold is. Do you see that? You see that? Okay. Now let's take ours and let's ladies and gentlemen, redefine our function here. So we're going to do def my join type parameterized. Maybe I'll call it type parm. How do I make this a type parameter? How do I make a type parameter now? Can anyone say? What do I need to put there? So if I want this to be able to apply not just to a list of double, but to a list of anything, I could put a square bracket. And then I'll say L is now a list of what?
T.
Of T. And str sep will still be a string. and it's going to return back a what? Okay.
It's a T? No, or is it a string?
It returns back a string, right? Okay, so how is this going to be different, ladies and gentlemen? How is it going to be different? Or can I copy everything from above down here as well?
Are we defining the new function?
Yeah, the new method. So how will this be different from the above one, if at all? Does this change? Well, just the name. Idna sharp eyes. Okay. 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 Okay, ladies and gentlemen. And we can then call, I believe we shouldn't even have to do that that T thing explicitly. We could just give it the list. The list T, str sep. There we go. And there we go. Okay. Now we've generalized this, have we not? Okay.
When you put H plus a string, does it automatically do the toString?
Yes, it does. It does toString because it recognizes that this is a string. Yeah. Okay. Okay. So we can join, monkey and horse, right? Sorry. What am I doing? List of these, right? List of these things: monkey and horse, and 1.2. No, you don't want to do that. Monkey and horse and
string 1.2.
Goat. Okay.
That's fine.
And then we'll put the string separator like this. Okay. There it is. Alternatively, ladies and gentlemen, we could have done,
Doesn't 1.0 work?
It works.
Sorry?
It works.
It should work.
Yeah.
Because it has a toString.
Yeah.
Yeah, but you shouldn't be able to mix it in the single list. Oh, of course it does. Yes, because it just treats it as any.
Yeah.
Anything
it's
that
just
has
not
a
a
toString.
meaningful list. Then.
Okay.
We're probably too complicated list.
Okay. Okay. There we go.
Yeah.
Okay. That's pretty nifty. So, ladies and gentlemen, let's take a look at this. Yes, it actually works. I thought Winchell was trying to get me to do something invalid, but no, this is a list of any, ladies and gentlemen. So pretty nifty. We've just generalized that function. Do you see how we did that? We've generalized it to operate on a list of any sort, not just a list, ladies and gentlemen, of a double. Good or not? Okay. Okay. Couple additional things. Time is a fleetin', and Dr. Doroshenko is a waitin'. So ladies and gentlemen, let's reason about this. Okay, algebraic data types. I mentioned that this is an algebraic data type. And there were some comments at the end about that. Basically, here we have a data type that could be one of either, for this list in here, either nil or a pair. And that pair could have a tail that it's itself a list, right? Do you see that in this thing here? So we say it's algebraic in part because we could express it as a sum. In other words, this, or this, in this case nil or this pair of products. And what's the product? Well, for nil, it's kind of a product with no pieces. But for cons, you have a pair of things. It's sort of one element crossed with, sort of joined with, paired with a list. Okay, so we could say informally that here a list is equal to either nil or the cons of some element. So a list of, I'll call it a list of t, cons of t. And now instead of writing cons, well, I'll write it like this, in a list of t. You could see how close this is to some of the definition here. Or I can write it as t cross list of t. It's kind of a pairing up of them. You have one of these and one of those. This is kind of a Cartesian product, meaning it's sort of a pair of them. All possible values of t, all possible values of list of, not list of a, list of t. There we go. Okay. Okay. So we've managed to do that through this kind of definition here, where we have a super type, and then we have subtypes defined. In one case it's an object, in one case it's a class. There's subtypes of list, and that can form up the list. Okay, we talked a little about companion objects. There's another detail having to do with so-called variadic functions.
Mm-hmm.
Now this is something where once again I think Scala has fallen short of its potential beauty. They could have used a few extra symbols on the keyboard and avoided this trouble. What do I mean by a variadic function? I'm actually not referring to variance like covariant, contravariant. What do I mean by a variadic function? It's actually talked about at page 34. What do I mean by a variadic function? I would argue that on page 30, apply is a variadic function. Why is that variadic?
Zero or more arguments.
Okay, zero or more arguments. It takes a variable number of arguments. Do you see that? And how is that indicated? With star. So ladies and gentlemen, let's read that. So if we apply, right, ladies and gentlemen, what are we doing here? So this is apply of something A, and we're basically taking in one or more A's, and it returns a list of A. So what are we doing here? What's the job of this function? What's his job in life of apply of A? Well, ladies and gentlemen, its job is to build a list. That's why it lives in the companion object. Remember I told you companion objects are used to like build up instances. Remember I said earlier when the session was yet young that I said up here. By the way, once again, I will continue my commitment to releasing the transcripts from these things in terms of the actual commands. But do you remember that I said like we could say list of this? This is a call. This list, this thing list, where is that defined? Where is this defined? Where is array of 2.0, 3.0, 3.14159, and this should be 2.71 by all rights. Where are these defined? Where is this array defined? Is it defined in the array class? No, it's defined in the array companion object. Companion object. And that's what that apply is. Ladies and gentlemen, this is defined as apply in the companion object. There's something called apply in the companion object for array that says basically if you call the word array with things in it, however many there are, that's what that AS colon A star is. It's not the A star algorithm. It's a list of A's. Okay. It's a list of, or sorry, it's not a list. It's a whole set of A's. And then how do we handle that? Well, we're building up that list there recursively, right?
Using pattern matching. So.
Well, this one falls a little bit short of pattern matching, but it says if it's empty, then it's nil. Otherwise, it's consing. It's creating a list where the first element is the head of it, and the rest of the elements are passed to the. They're passed to apply for the next thing. This as.tail, it turns it into a variadic list. There. Okay, that's what that is. It's kind of passing the rest of them as a function argument to itself to apply. So once again, this is recursive. It handles the base case where it's empty, and then it handles the case where there's at least one and passes the rest to itself to apply. So it breaks it down. Divide and conquer. Okay?
So how does it know how to do the function .head.isEmpty.tail on a list, but not a list?
Scala provides us it the ability to do that. So when you have a variadic thing like that, it has operators on it, like isEmpty and head and tail.
But in this case, AS is not.
It's not a formal data type.
It's not a data type or data structure or anything.
No, but Scala treats it as a data type for the purposes of writing
sort of
the code.
So there's an underlying constructor where it creates a data type.
And I can't remember. I think it does have some underlying representation. That's right. And so these things are defined on variable lists of arguments. Like
so it's a bit like it's translating one data type into another data type. So it creates a basic one just so it can navigate through. And
exactly. Yeah. Exactly. Yeah. Okay. So, ladies and gentlemen, we're going to need to end the Dora wait soon. So, there was a mention that type inference is limited within a given parameter list, but you can divide it up into successive parameter lists in order to do type inference. And I'm searching for the page. I won't spend long on this, but it's on page 37. It says it's a little unfortunate that we need to specify what the type of X is. The type of X is int here, and the point is that in doing type inference, if you have a function, in this case drop while, which takes a list of A and then a function from A to Boolean, it's not going to be able to figure out, you passed a list of double, so the function must be of doubles. You actually have to be explicit, or a list of ints, so you're going to provide an int for the next function. But if you divided it up into two, if you curried it, it would be fine. If you curried it into two parameter lists, so took the list as the first one, and then the next one took the function, it would be actually, okay. We learned about tuples a little bit. Tuples. How do we create a tuple, ladies and gentlemen? I'm going to create a tuple of monkey and 3.14159. How do we create a tuple?
Just square root brackets.
Yeah, we just use these. Monkey and 3.14159, right? There we are. Okay? Yeah. Okay. Okay, there's a special Scala syntax for list with that colon thing. I would note here, ladies and gentlemen, in case as a peek in the future, you can create, so just as you can create monkey things like this with this, here's monkey, horse, and nil, right? Nil. We saw this earlier. Just as we can do that to create a list, I would say you can create a stream by doing similar things. Okay, but it's with this, and I actually don't even think you need this. Okay, you do. Okay, So monkey, I think Dr. Doroshenko is, oh, there's how, okay. Okay, okay, no. Not a member of list, okay, so can we, oh man, I'm screwing this up. There's a way to do a similar thing with a stream that's quite nice, and it would define, okay, list of so my stream equals stream of 2, and then you can have, for example, my stream 2 equals monkey here, and do this, and then do my stream. Okay, there. Oh, my stream. Sorry. Okay. So what is? Okay, monkey. What did I do here? Okay. Oh, of course, it has to be a stream of the same sort. I can't do it with a stream of 2. I have to do it with a stream of 3, then, or another number, because my stream is of ints. Alternatively, I could have said my stream and my animal stream. How do you like that? Animal stream, and I could have said dog or horse. There we are. And then I could have said my stream 2 or my animal stream 2 equals monkey and my animal stream. Okay, animal stream. Boom. Okay, ladies and gentlemen. So there we have my animal stream, and if we were to go force it, we could. This is a stream which we'll use, but this is lazily evaluated. But if we want to see all of them, here are the monkeys and horses. Okay. Okay. And then different naming conventions. Yeah, there's a different convention for naming things in functional languages. They tend to use short variable names, and the functions tend to be more abstract for that. Okay, we've ran out of time. I suspect Dr. Doroshenko awaits, and I'd be glad to talk with students who would like to discuss things now. Okay. Great. Okay, so that's all for today. For next time, we are going to read the next chapter, Handling Errors and Exceptions. This chapter, I think, will give you more to think about yet, and has profound implications, and I'd encourage us to go through it as long as it takes. So we might spend two times on it. It will be a bit challenging, but it's about avoiding a $1 billion mistake.
More than.
Yeah, I'm not talking about avoiding Donald Trump. I'm talking about avoiding null. Null. Yes, it's probably more than $1 billion. That it's damage it's caused. Okay. So hopefully Hillary Clinton yesterday avoided another multi-billion dollar mistake or $1 trillion mistake. For those who didn't see it. Okay. So that's all for today, and we'll reconvene next time discussing Chapter 4 on Thursday. Okay? Thank you very much. Yes. Yes. So yeah, I tried reaching Dr. Wong. He had invited me to call him over the weekend, but I couldn't reach him. Give me just a second here. So I'm keen to find alternatives.